Hello, I'm Jonathan Medachin, and I'm going to be giving a talk on chaos and iterated functions, beauty in complexity. So here we go. So chaos. Beautiful pictures like this can be formed from very simple functions, and I'm going to explain to you all how we can do that. I'd also like to start by thanking you all for coming here and listening to all this jibber jabber. Here we go. No, you're not liking me now. Okay, some sort of technical difficulty. It's not going to the next slide. There we go. Okay, so functions. A function is very basic. For a function, you put a number in and you get a number out. That's how a function works, and that's what it does. If you put a number in, you will never get out a different number. You will only get out the original number. Every time you put in the number, you will only get out a unique answer. You'll never get out two separate answers. And if you put in some numbers like 0, the function will explode, and then you'll have infinity or negative infinity, and it'll be really unhappy, and it'll really not like you. So, iterating functions. Now you iterate a function by putting in a value and getting the value out. Then you take that value and you plug it back in and you get out another value. Take that value, plug it in, get out another value. Now notice here that we put in 2 and we got out 2. Now from the previously stated rules, because 2's got put out 2, it can never put out anything else. So when we take 2 out and put it back in again, we get 2. This is called a periodic function. This 2 is called a fixed point in the iterated function. Because once you land on 2, you're going to stay on 2 as you continue iterating that function. So, here's another example. We put in 4 and we get out 1. Now we put in 1, we get out 8. Now here's the interesting part. We put in 8 and we get out 1. At this point, we put in 1, we've gotten out 8, and we put in 8, we get out 1. Now we have a loop forming, and so an orbit is the set of numbers that includes your starting number in an iteration and all of the future numbers as you iterate it, all of the iterates after 4. So the orbit of this particular function, starting at 4, is the set 4, 1, 8. So although the gear and the arrows are very nice visuals, us mathematicians don't really like doing things like that, so we have this format like this. F of 7 is 3. Even more general, we have x sub 0 for our starting value, and x sub 1 would be the next value that we use for the function. And even more generally, we use x sub n and x sub n plus 1 to indicate the next value in the iteration. So, x squared, basic function, plotted on the Cartesian plane, rather simple. So, here's the x squared function. Notice the x squared function in red, the square root of the square root of x in blue, and the square root of the square root of x in green. So, as you notice, in the red, we go from the order red to blue to green, and for values greater than 1. And for values less than 1, we go from red to blue, green, ascending. These values are actually approaching the line 1. As you see, they get closer and closer, and here they get closer and closer. Also, you'll notice that the orbits of this function have 2 fixed points. If you start at 0, you'll end at 0 because the square root of 0 is 0, and the square root of 0 is 0, 0, etc. So, and also the point 1. So, these orbits are attractive orbits. The orbits for greater than 1 and less than 1 attract asymptotically to the value 1. As you can see, if we start with 4, well, square root of 4 is 2, and then 1.4, and then 1.9, etc. And in the absurdity, if we did this an infinite number of times, we'll eventually get to 1. They can also be orbits can also be attracted to points instantly, as in the case of 0 and 1. you simply start iterating 0 and then you get 0 and you stay there. Orbits can also be attracted to points slowly. This can either happen because the orbit jumps around a lot and never really lands on a number, or, well, it jumps around a lot and eventually gets to a number, or if it just takes its time linearly getting there. Orbits can also be quickly attracted to fixed points through either linearly or exponentially. So here we have the x squared function in red and the others in their respective colors. And as you'll notice, for values between -1 and 1, not including 0, we have the order red, blue, green, and the values approach 0 as we iterate the function. And also notice that this function has 3 fixed points, -1, 0, and 1. But more importantly, you can notice that for up here, we have the order red, blue, green going in the other direction and actually up. And so this means that this function is going to escape as we iterate it. All the orbits, besides those started in this range, will go to infinity. So for example, 2, you get 2, 4, 16, and then eventually that orbit will go to infinity. So the function 4 minus x. So here in red is 4 minus x, and here's the other guy. But you may notice there's no green function on here. And that is because the green function, algebraically, is actually equivalent to the first one. And so the green line actually is over the red line. This indicates that if we iterate the function, we are actually going to be returning to the initial values by the second iteration. So this is an example of a periodic orbit. So let's take 1. If you put in 1, you're going to get out 3. And if you put in 3, you're going to get out 1, and it's going to hop back and forth. This is a strictly periodic function because it's just going to hop back and forth between 2 integer numbers, and it's nice and simple. But there are also orbits that asymptotically approach being periodic. One case is this guy right here. If you take him and you look at its orbit starting at 4, you get 4.6 and all this blah, blah, blah. It's kind of hard to see. So I'm going to graph it for you. So here, we have 4, then 0.6, then 0.96, and so on and so forth. And as you can see, it looks like it's going to be repeating itself. But this orbit never actually takes on the same value twice. And so it gets closer and closer to repeating itself, but it never actually does. This type of orbit is sometimes referred to as a chaotic orbit. And so that brings us to chaos theory. Now, this kind of surprised me, but we actually have a definition for chaos. I didn't really expect there to be one, but here it is. Chaos theory is a field which studies the behavior of systems that are highly sensitive to initial conditions and whose outcomes are greatly affected by the smallest alteration. So this is sometimes referred to as the butterfly effect, because apparently weather systems are so very sensitive to initial conditions that a butterfly flying by a spot a week beforehand can affect the precise location of where a hurricane might form. So, up to this point, we've been dealing with the Cartesian plane, but we are now going to be progressing to the complex plane with real numbers on the horizontal axis and imaginary numbers on the vertical axis, and we'll be dealing with the functions q of z. So, what we're going to do is we're going to take a given function and we're going to input a value in it to start the orbit. That's going to be our initial value. And we're going to plot it. So it's going to have a real component and an imaginary component. And if that value in the orbit tends to infinity, we're going to color that point red. Now, we're going to take another point, and if that point stays bounded in its orbit, we're going to color that point black. So again, if the orbit escapes, we're going to make it red. If orbit stays bounded, we're going to make it black. Most of these functions are going to have the form z squared plus c. Our first example is going to use c is equal to -1. This forms this picture right here. Now, as you can see, it's quite complicated, and the point D actually will escape and go up to infinity if you chose that point. The complex plane is actually lines that are not shown. And as you can see, it looks quite chaotic. This one's actually called a basilica. So here's another example. This uses a simple function z squared plus I and iterates it with different starting values. As you see, it looks like a neat lightning bolt. This is a rather famous one, the Dowdy rabbit, using this equation here. As you can see, it looks kind of like a fractal, because you can see smaller versions of it as you go along and zoom in. But here's where it gets interesting. So this is the Dowdy rabbit with this extra variable, extra component added in. The inside here is basically chaos, because if you take a starting value and take the orbit and see where it goes, it might go to infinity, but then you move a little bit to the left and you take your starting value and it'll stay bounded. So just these tiny alterations in your starting values can determine whether you blast off to infinity or stay realistic. So, no talk on chaos would be complete without the Mandelbrot set. This image is formed slightly differently than the others. This is formed by only using 0 as your starting value and instead varying the complex component c. So for different values of c, you get you either go out to infinity or you stay bounded. So, starting with functions and merely iterating them, taking the value out and plugging it back in, and because the fact that functions can be incredibly deterministic, functions are incredibly deterministic, but the slight changes in their starting values can eventually lead to chaos. Thank you very much.
Thanks. I have a question.
Yeah.
It's a very interesting topic. The topic is perfect squares.
What?
Now, the topic is chaos and iterated functions. Perfect squares was last year.
Oh, it is, because that's what I'm seeing on my little thing that they gave me here. Oh, okay, okay, well, that's nice to know. Is that what you have down there,
Iterated
perfect
functions,
squares?
chaos is
Yeah, okay.